Welcome to the deep dive. If you are tracking the modern night sky, you know astronomy is currently, well, it's a chaotic fire hose of data.
It really is.
Telescopes produce millions of alerts every single night, promising this cosmic treasure like a rare supernova, but most of those signals.
They're bogus.
Yeah.
Just noise, streaks, maybe instrumental artifacts.
The stale is just, it's impossible for humans to handle alone.
Historically, we definitely relied on artificial intelligence, on AI, to manage this volume. For years, the standard was fast, specialized systems, CNNs.
Convolutional neural networks.
Right. They gave us incredible speed, which was needed, but they functioned as complete black boxes. Meaning they'd stamp an alert with a score, say, 0.9 for real, but they couldn't tell you why. And if you're a researcher, trying to defend a big discovery or even just train a new team member, that lack of context, it creates a massive trust deficit.
You need the proof, the reasoning.
Exactly.
Which brings us right to the core mission of this deep dive. We've been looking at sources detailing this international team's experiment using a general multimodal model, Google's Gemini. And their breakthrough idea was kind of simple but radical. Can an AI not only classify these transients with expert accuracy, but also explain itself, give clear, text-based reasoning?
That's the key.
So we're unpacking this shift reported in Nature Astronomy, moving from just opaque scores to, well, transparent collaboration.
And what's really fascinating here is the methodological shift. It's away from that traditional data hunger idea in AI.
Right.
The team realized the goal wasn't just brute force memorization. They used something called few-shot learning.
Few-shot.
Yeah. Instead of feeding the model millions, maybe billions of labeled images, they focused on curation. They gave it only 15 high-quality examples for each survey.
15? Just 15?
15 per survey. But they were really well-chosen examples paired with clear instructions on how a human astrophysicist actually thinks, how they reason.
That few-shot approach, it really does sound counterintuitive, especially now in the age of big data. Was there pushback? Like, only 15 examples to define a supernova?
Well, it definitely goes against the usual machine learning playbook, but the results really validated it. The thing is, the base model, Gemini, it already has this vast general knowledge.
Okay.
So the small guide set, it just provides the specific astronomical context needed. And critically, the input itself was designed to teach reasoning. For every alert, the model saw a triplet cutout.
Which is what exactly?
Okay, so first, the new cutout. That's the image showing the alert itself. Second, the reference cutout, an older picture of the exact same patch of sky before the alert.
Got it.
And third, the difference cutout. That's simply the result of subtracting the reference from the new image. It isolates the change.
So it highlights what's new.
Precisely. By pairing this visual data, the three images, with crisp expert notes and instructions, they basically taught the model to look for significant differences, not just, random bright spots.
And this approach held up even though they used data from three really diverse surveys: Pan-STARRS, Mirlicht, and Atlas. I mean, those instruments have different resolutions, different cameras.
Totally different. Varying pixel scales, unique camera artifacts, the works. And that's probably the most compelling evidence that this achieved real generalization.
How so?
Despite those visual differences, like the same object might look kind of blocky in one telescope and much smoother in another. Gemini kept up high accuracy using just that small guide set.
Wow.
It strongly suggests the model learned robust, compact rules that can actually travel across instruments instead of just memorizing image templates for one specific setup.
That resilience sounds vital in astronomy. Things are always changing, new instruments coming online.
Exactly. It's crucial.
Okay, so here's where it gets really interesting for, I think, any scientific field. The real win here is the explainable AI part, right? Generating output that sounds like a scientist.
Yes. It justifies its classification call real, bogus, variable in plain language. It describes exactly what it sees in all three frames: the new, the reference, and that crucial difference image.
So it turns a simple score into like a mini report. We're working hypothesis.
Exactly. That explanation is the product. And it goes further. Beyond the basic classification, the model assigns an interest score.
To help prioritize.
Immediately guides follow-up priority. And even more powerful, that justification text creates what they call a searchable narrative.
A searchable narrative. How much faster is that? Querying text versus, scrolling through thousands of images or just sorting by score. Does this change how astronomers catalog things?
Oh, it absolutely changes the game, massively. Instead of dealing with these opaque scores, scientists can now query the catalog by content. They can ask things like, show me bright circular sources on a faint galaxy background with a positive difference residual.
You can be that specific.
Yes. That narrative acts like a rich, annotated catalog entry. It makes the whole vetting process human auditable, searchable. It really respects the human process of scientific reasoning.
And the team also built in a safeguard, a safety rail, they called it.
They did, a critical piece. The model wasn't just asked to classify. It was asked to check its own work.
How does an AI check its own work?
Well, for every single output, Gemini scored the coherence of its own explanation on a scale, 0 to 5. And it checked for internal consistency. Like, did the detailed text justification actually match the high-interest score it assigned?
So it's basically raising its hand when it's feeling unsure, or when its own story doesn't quite add up?
Pretty much. It's like self-awareness, or at least a form of self-critique.
Okay, how useful was that self-checking in practice? Did it actually help the workflow?
It was a massive advantage for triage. Huge. They found that low coherence scores were really strong predictors of actual errors. So this lets researchers triage by uncertainty. They can route only the hardest, the least coherent cases, the ones the AI itself flagged, to the precious human expert time.
Makes sense.
And using this uncertainty loop, refining the instructions based on those low coherence cases, they saw performance jump significantly. Accuracy on the mirrorless CHT set, for example, went from about 93.4% up to around 96.7%.
Wow, that's a big leap.
It's a massive gain achieved through, well, logic and refinement, not just throwing exponentially more data at it.
Let's look at those quantitative results then, because they do seem to set a new benchmark for AI image analysis, especially when you don't have millions of labeled examples.
Right. Across those three diverse data sets, remember using just 15 examples per survey, Gemini achieved an average accuracy near 93%.
Which puts it right up there with the traditional CNNs.
Squarely in competition. And those CNNs were often trained on significantly larger, heavily curated beta sets.
Just to anchor those numbers for you listening, we saw really consistent performance. ATLs, 91.9% accuracy. Mirlic-T, 93.4%. And Tanstars, 94.1%. They hold up remarkably well across different instruments.
And to help others replicate this, the team published this really detailed 8-step field guide. It shows how structured and deliberate the whole prompt engineering process was.
Let's walk through a couple of those steps maybe to see how it works.
Good idea. Let's look at the first few because they really define the AI's operating environment.
Okay, start us off with step 1, the persona.
Right. Step 1 is the role. It's foundational. You define the model's persona. You literally ask it to act as an experienced astrophysicist.
Like role-playing for AI.
Kind of, yeah. And you embed the expert rules directly into the text prompt. This is where you describe the telltale signs of a bogus alert, things like satellite streaks, diffraction spikes from bright stars, or that classic misalignment artifact known as the Yin-yang residual.
Wait, back up. What is a Yin-yang residual specifically? That sounds interesting.
It's a key bogus artifact you see in the difference cutout image. When the two images, the new one and the reference one, aren't perfectly aligned before you subtract them.
Okay.
A point source, like a faint star that hasn't changed, doesn't just disappear completely. Instead, you get a small, perfect bright spot right next to a corresponding perfect dark spot.
Ah, like the symbol.
Exactly like the yin-yang symbol. It clearly indicates misregistration, a technical glitch, not a real new celestial event. So by specifying that pattern in the prompt, you're encoding decades of human observer expertise.
So you're basically translating that hard-won human expertise into text instructions for the AI, programming its judgment.
That's a great way to put it. Then step 2 is selecting the guide set. That's curating those crucial 15 balanced examples, real transients, variable stars, and clear bogus cases focusing on clarity and strong representation, not just sheer numbers.
Quality over quantity.
Absolutely. Then comes step 3, the contract. This is vital. They demand a strict JSON output schema.
JSON, so structured data output.
Yes. It's critical software hygiene. It ensures every single output is immediately machine readable.
Meaning it plugs right into existing astronomical databases. No manual work needed to parse the results.
Precisely. The response must always include the classification, the text explanation, the interest score, and that crucial coherence score we talked about. This discipline structure guarantees the results are reproducible and immediately useful in, like, a real production environment.
Okay, now, we do need to touch on limitations. A big general model like Gemini, it's inherently slower than those custom-built CNNs designed purely for speed. Right.
That's true.
If you're trying to process 10 million alerts a night, which is happening, relying purely on the large model, it's just too slow for that initial bulk processing.
Absolutely. And that's where the final step in their guide, step 8, provides the practical solution. It's the hybrid approach.
Hybrid.
Yeah. Use the fast CNN or maybe even a simpler heuristic filter for the bulk triage, just to knock out the obvious garbage alerts really quickly.
Get rid of the easy stuff first.
Right. And only send the small subset of candidates, the ones deemed interesting or genuinely uncertain by the fast filter. Only send those to Gemini for the full, detailed textual readout, the explanation.
Okay. That makes perfect sense. You get the best of both worlds. The speed of traditional AI for the massive data fire hose, and the clarity, the reasoning, the trustworthiness of the multimodal model for the really high stakes or nuanced candidates.
Exactly. It's a synergistic approach.
And this framework, it clearly extends way beyond just astronomy, doesn't it?
Oh, for sure. I think it's a blueprint for Gemini in science, really. Yeah. Any domain that pairs complex visual data with required expert judgment, think medical imaging, pathology slides.
Geoscience, maybe? Looking at satellite images.
Geoscience, materials microscopy, satellite change detection. Anywhere you need an expert eye and an explanation. These fields benefit immensely from systems that can explain themselves and transparently flag their own uncertainty.
So the core takeaway here seems to be that this approach successfully brings together classification, reasoning, and that uncertainty check, the triage, all in one clean, auditable loop.
Yeah.
It really makes the case that the text, the explanation, isn't just some friendly garnish added onto a score. It's fundamental. It's the substrate for human collaboration with the AI.
I completely agree. The breakthrough isn't just that the model spots the bright dot, the potential discovery. It's that it explains why it thinks it's important. In language, a human can actually check and understand, and it signals when it's unsure.
It's collaboration over just pure automation.
That's the goal, moving towards genuine collaboration.
So what does this all mean for you, the listener? Whether your field is hunting supernovae or spotting microscopic anomalies, this framework seems to demand that we treat the prompt itself differently, like a living artifact, they called it.
It's not a static instruction set you write once and forget.
You have to keep iterating, right? Feeding back those low coherence cases, the tricky examples the AI struggled with, to constantly sharpen its reasoning.
Exactly. And that really gets to the ultimate goal here for astronomy teams, and probably science generally. When you can trust the machine's reasoning, not just its score. Scientists stop spending their precious time just vetting thousands and thousands of ambiguous alerts or scores. They can actually focus on asking the next good question, formulating the next scientific hypothesis. It just accelerates the whole pace of discovery.